Welcome back. Are we ready? Good afternoon. We had a very fascinating morning session with the presentation of 6 excellent projects for the explorers, and we're looking forward now for the presentation of the finalists in the pioneers category. We have 9 projects from 9 countries, and we are going in the first session to present. We're going to have a break. Firstly, we are going to present the first 7 projects, and then after the break the last 2. So we are ready to start with the first one, which is the project AstroVianu Lab from Romania, and is by a team from AstroVianu National High School of Computer Science, and they are presenting Andrea Zaharia and Vlad Panait, and her teacher coach is Miss Ioana Stoica.
Thank you very much. Hello, we are AstroVianu Lab from AstroVianu National High School of Computer Science in Bucharest, Romania. I am Vlad, this is Andrea, and today we are going to present our project to you.
Excited to research planet exploration, we set our mission to determine whether a certain planet is habitable or only exploitable in matter of resources. Regardless of the type of that planet, we are going to explore the universe further, so that we are going to attempt exoplanet detection.
In order to accomplish each of these goals, we have conducted research by studying other rover missions such as Curiosity, creating handmade spectroscopes as the one you can see over there or the one on the rover, and also testing and comparing different data sets that we were able to gather with our sensors.
Closely observing the Curiosity's scientific instruments, we have distinguished 4 major categories: cameras, spectroscope, radiation detectors, and environmental and atmospheric sensor suites.
So, taking all this in consideration, we thought that our rover has to be able to gather different parameters that are going to tell us whether a planet is habitable or only exploitable. These parameters are as follows: the percentage of methane, because methane is a gas that is very important to human life. Also, the quantity of UV radiation, which can be harmful to human life. Also, the rover is able to spectrally analyze the atmosphere of the planet it is studying in order to tell which gases the atmosphere is made out of. And also, the rover needs to be able to tell more about weather conditions and take pictures of the planet.
With such data, we can obtain a very in-depth analysis. For example, let's take Curiosity. One of the most important discoveries of Curiosities is the Yellowknife Bay on Gale Crater on Mars, where scientists concluded that there has been an ancient lake as home for chemolithoautotroph life.
Okay, so having all that said, we wanted to build a rover. So, having had previous experience with sensors, the first thing we did after we built our rover was to test if the sensors were properly calibrated. So we tried and calculated the density of air through 2 different methods involving all the sensors, and we obtained the same approximate value, 1.43 and 1.44, which means that our sensors were properly calibrated. Another aspect that came into our minds when testing the rover was how would the behavior of our rover change on a planet with a different gravitational attraction than Earth. So we attached helium balloons to the rover, in this way creating an upthrust and trying to simulate the lower gravitational pull on Mars, for example. So this here you can see us attaching balloons. The effect of the balloons is that the stress on the chassis is lower, as well as the frictions of the wheels. This is why we conducted research on this theme. In order to not modify the rover's behavior, we attached the helium balloons to the center of mass, which we can see here we've calculated after measuring all the rover's dimension. Here in this video you can see our rover in our high school's backyard sandpit. It is a video taken while we were gathering data, which you can see in the next slide. Our sensors are able to capture pressure, temperature, UV radiation, light intensity, and methane concentration of the air. Here you can see a table of a data set. That on the top right is the first picture that our rover was able to take. And here this plot shows a 24-hour test in which we looked at the light intensity that our rover is able to measure in order to determine when a storm hits Bucharest. Because of the nebulousness, the intensity of light dropped.
Endeavoring to get to the analysis project process that's following the data acquisition, we try to confront two data sets gathered in Romania, one in Bucharest and one in the mountains. We can see that in the mountains the temperatures were lower due to altitude, rainfall, nebulousness, and also the pressure values are lower in the mountains, and we've determined a thinner atmosphere. In the hot days in Bucharest that have been recently, we've had the idea to bring our rover and measure with all the sensors. Then, contacting a local medical center, we have found out that a lot of people have presented with skin and eye problems, a much higher number than usual. Here are the values we gathered. Here is in direct sunlight. We put our rover in a direct sunlight area and let it measure, and then in a shaded area. There's a tiny difference in temperature, but the most interesting one is in luminosity and in UV intensity. In the plot, you can see with red the direct sunlight points with UV intensity, with blue the shaded area, and with yellow is the value 0.6. The value 0.6 is the value starting with which people start to encounter problems, skin and eye problems. It's starting with pains and slight discomfort and can get to erythema.
Okay, during the recent tests, we noticed that our initial chassis, which was the one you saw until now, encountered difficulties when traversing different obstacles. Like in this picture, when it tumbled over because it couldn't get over the rock. So we were interested in changing the chassis. And we wanted to see which would be the optimal height for the chassis so that the rover would be able to safely go over obstacles while also maintaining its stability. This is a picture where you can see in the front it's the old chassis, the smaller one, and in the back it's the new one, this one, much bigger. So for a given magnitude of velocity and for a given magnitude of curvature radius, the height of the chassis increases the rover's instability. This is why. Okay. Now we are going to talk about our spectroscopy and the spectroscopy part of our project. So now we have developed our spectroscopy module, this one. So what we want to do from now on is to further develop and maybe be able to detect and study exoplanets with our spectroscopy, and also help improve different scientific equipment. So why send this planetary rover with a spectroscopy module attached in complement to spectroscopy is light pollution. So if we were to, let's say, send this rover to Mars, that would no longer
Pi 2B, a Raspberry Pi camera, and the spectroscope built by us. The first spectroscope we built was this one, using a kit received by our school in the NASA program Weather in Space after a successful participation. Then we've started our research, went more in depth in spectroscopy, and created the spectroscope you see over there. Now, with the software we've written for the Raspberry Pi, it takes pictures through the spectroscope every 10 seconds.
Okay, so we liked the idea of spectroscopy, and so we experimented. We used our high school spectral patterns. So in these pictures you can see the sodium spectrum, the methane spectrum, the daylight spectrum, and the mercury spectrum as we obtained them through our spectroscopy module.
Exoplanet detection. Exoplanet detection is hard to achieve with direct observation. That's why scientists use indirect methods. One of the that's considered one of the most efficient ways, and also the most widely used nowadays, it's transit photometry. In transit photometry, the most important are the 3 stages of a planet passing in front of its parent star. In the first phase, in stage 2, the planet starts to gradually occupy space in front of the star, hence dimming it gradually. In the third phase, the planet is completely in front of the star, and we can see almost constant animation we created to our colleagues at our school, since we love to research, but we also love to share our experience, our experiments, and we've made this for them to better understand the light curve. Also, since exoplanet detection needs a photometer, before implementing it with the Arduino with the visible light sensor, we've created this simulation with an Arduino board, the sensor, and a display to show the light intensity and lux, where we are sliding the intensity over there from shaded to sunlight.
Okay, this would be all. Thank you very much for your attention.
I like this very much, very much.
Thank you.
Just had a little problem at the end that because I didn't understand completely what the exoplanet detection was doing here.
Let's take another example of a space mission that even if it's focused on a planet, it looks to another too. Let's take Cassini. Cassini is orbiting Saturn, but also one of his targets is to take a distant picture of Jupiter. It would help scientists a lot to know more about Jupiter, to improve scientific instruments. That's why we're attempting here too. We have exoplanet detection since we are away from the artificial light pollution we have on Earth. We can see better from a distant planet. We can look further. We have cameras, sensors that can see better from further without the pollution here. They look, they see, we detect exoplanets, and we can know more about the universe exploring. So it's not only about exploring the planet we are on.
So, is it, in your opinion, it's better to have the exoplanet detection on a rover on the ground than in orbit on a satellite?
As long as we have a rover on the ground, I think we should use all the methods we can. We can add these instruments to develop as much as possible and try to obtain relevant data in all the fields it can return.
Yes, I agree with you. But in order to bring the rover down to the ground, you need to have energy to land it. So that energy you usually want to save by keeping as many instruments in space as you can use in space. So if there is not an additional value of having the exoplanet detection suit on the ground, then I might be tempted that the satellite would also be a good and maybe a cheaper solution and safer, because you don't have the risk that it crash lands. Yeah. But nevertheless, it's a very nice rover development. I have one question. On one of the slides, you indicate that you measured temperature in Celsius. On the other one, you measured in Fahrenheit. Was it just a typo, or did you actually mix both? Because that would be a big sin. Huh? We have lost spacecraft because of Americans using their units and Europeans using standard units. And
No, it wasn't a typo for sure. That's why we specified the units in every table, everywhere.
I strongly discourage you to use two different types of measurements. One measurement using two different units, because that leads to error, and that will trickle down in your projects somehow later on.
So next is a project from Portugal. It's called LEARS, Learning Robotics in School, by a team from Escola Secundaria Sebastião e Silva, and they are presenting Carlota Fernandes, Diogo Gonçalves, Nelson Rebelo, and the teacher course was Miss Cristina Pino.
We're just waiting for the Prezi to load. Okay.
It's loaded. Great.
First of all, we are really sorry for the delay. Good afternoon, bonsoir, boa tarde. Our team name is Future Robotics. My name is Carlota Fernandes. I'm 17 years old, and I am a person with lots of different interests, going from drawing to sports to music to maths. That's the reason why I am an economics student and at the same time member of this team.
My name is Diogo Repas. I am a 17-year-old science and technology student. I've been interested by the world of computation and programming for over 7 years now. So now I'm just an addict for the technology, innovation.
So, hi, I'm Nelson, and I'm 16, and I'm also a science and technology student. And I consider myself to be a root entrepreneur somehow, and I'm since my young age inspired by the field of electronics and of space as well.
Our project is based on the construction of a rover, LEARS, which means Learning Robotics in Space, which is capable of gathering environmental data among other functions. We are from Lisbon, Portugal, and our school is High School Sebastião e Silva in Oeiras, and there is our head teacher, Professor Domingos Santos.
Okay, so the concept about this rover. We knew about this project, this amazing opportunity, through our teacher, Christina Ping. And soon enough, we started thinking which would be the most innovative and original way to coast the team of space. We came up with the idea to build this entirely functional rover with little to no time, money, or even knowledge. We all agreed and said that this would be our project.
So why a rover? Not only it would allow us to approach themes that inspired us since our childhood, but also because this was a theme that was completely unknown to us till this project. Lastly, because the rover is the eye of the man in the unknown, so it's the most safe, the most reliable, and the best way to explore the universe. On the other hand, we took this project to prove a point. Space exploration is at reach of each and every one of us. You just need to have the passion and the determination that we have.
So, first we had to define our goals. We wanted a remotely controlled motorized vehicle with a myriad of data gathering sensors. We have implemented light, temperature, gas, ultraviolet intensity levels, visual data with a camera, absolute orientation or attitude, GPS position, among others. It was an ambitious project because we never had any lessons of some sort about this subject. So we started to schedule and divide our project in many steps, and each step in several tasks. And we then named a person to be responsible for the coordination of each task. We faced several obstacles, such as our tight budget, which really limited our material choices, or the lack of basic mechanic skills, which we overcame with the help of professionals in this area and the 3D designer who helped us build the three-dimensional computer model of our ideal rover.
Early in the project, few companies, whereas local authority and our school, showed lots of interest in our project, giving us the materials and the technical support that we needed to improve even more our rover. Then we had a field trip to the Institute of Systems and Robotics to the goal of acquiring new knowledge and our mentor, Professor João Sequeira.
So, at this time, we started building our first prototype, aiming to test different concepts of locomotion and coding. With this effect, we decided to use LEGO, a platform in which we happen to have more than 16 value diversified years of experience. And with this, we intended to test different concepts, as I said. And with locomotion, we went with gradual testings, going from the simple wheel to a more complex concept like the Swedish wheel, and concluded that the triangular caterpillar would be the most effective concept to use in matters of energy and balance, aiming to the goals that we had set up and to this concept. After this, we started having weekly meetings both at our high school and the ISR that aimed to clear out some doubts, to smooth out some edges, and to put everyone on the same page about what we were doing.
After weeks of hard working, our first prototype was concluded. Then we submitted our application form to Odysseus and started advertising our project, where we got an astonishing reaction. Our video on YouTube got over 1,000 viewers and was published by distinguished entities. One of the main lessons that we learned with this project is that if you show the passion and the effort, all help comes naturally. That was happened to us. Following that, we felt like we couldn't stop here. So, with the help of a professional engineer in Algarve, we developed even more our rover with the chassis according to the 3D model.
So, then I guess we won the regional phase, and we couldn't believe that we had won, but we did. So we started working, believing that we could further develop our rover. To do that, we aim in two main subjects. Prepare the rover for space exploration and give him the ability to have a life detecting system. And also, we decided that we could, some of the goals that we had set up on the regional phase to the future, we decided to development and to make it work.
To sum up, we added UV, gas, and ultrasonic sensors, which allow us to gathering even more environmental data and detect obstacles and which distance were we from them. We design our graphic interface, making it more more accessible and more easy to look for the data.
Okay, now I'm going to talk you a little bit about the coding. We did all the coding ourselves. We never had any prior lessons or classes on this subject. And this is a small schematic of our codes. We use C++, a high-performance programming language, and started by developing a first program to test each component and its functionality. We then erased that one and raised a new one from scratch, with the objective of creating a more modular and structured codes. At the heart of our program, it's Qt, a framework used to create elaborate and complex GUIs, graphic user interfaces. We also have a library set called OpenCV, which contains tons of computer vision algorithms, which allow an effective communication with the camera and opens many doors in the world of computer vision. In total, we use 2 programming languages, C++ on a computer for its speeds, and Python on the rover because of the amount of available documentation online and the ease of use with the sensors. We wrote, at the regional phase, we had written 25 functions, 95 variables, 700 lines of codes, and spent around 400 hours programming. These figures have increased to 230 and almost 1,050, 1,500 in just 1 week, because we had our final exams, our national exams, in these few weeks between the regional phase and the final. Okay. Now we'll demonstrate the rover. This is how how the graphic interface looked at the original phase, and this is how it looks now. And it may look simple, well it should, but behind its simplicity it's doing many complex tasks, which make it a complex brain. We'll now demonstrate is walking around, gathering some data, and it is remotely controlled, so we can be here, there, it can be in Japan. We would still be able to see what LEARS is seeing and feel what she is feeling with her sensors.
So let's begin. Does anyone wants to volunteer? No?
Can
Okay.
we force speak you? Okay.
Fred?
Okay. No. Stay here. Stay there, please. Okay. The rover will come to you. When it starts, of course.
Well, we all this fuss about we're getting late, and it was all due to a few problems we faced during the flights. Because what happened is that during the flight many of the components and cables got damaged, and we had to fix that. We stood up all night awakened to fix some problems. We even created a battery using tinfoil and glue to try to put the motors to work. We haven't yet tested that battery. We'll just hope it works. So let's see. As you can see, you have light intensity in lux. You have the temperature in Celsius, the pressure, the ultraviolet index, the gas sensor. It is sensing normal air, but if you light up like a cigarette, a lighter near it, you can see it shows some values, and we have the distance sensor. When it's showing -1, it's just a small indicative of out of range. It is not within the range of the sensor. If you try not to light the lighter but just press the gas, then it would be better. Carlotta, near the gas sensor, isn't it working? Yeah, but if you get really near, it shows some toxic levels to the human eye, to human life. Let me demonstrate. Well, yeah, that's it. Well. You can also test the light sensors. You can close them, and as you'll notice, there are more than one sensor of each kind for redundancy. In order, if one fails, we can still have the data from the others. We have a graph here. This graph shows only temperature and pressure. We also have the roll, pitch, and yaw. You can show it.
No. Just like there.
Yeah. And it has a compass. You can turn it like this, and you'll see the compass changing. Well, we also talked about computer vision earlier. So we want to demonstrate it also can recognize faces in an image. Why faces, you asked? Well, there are not many faces in Mars, but this is a proof of concept. We didn't have the tools needed to train it to recognize more important features, such as rocks and their type of rock. But, well, let's try to... Wait, it's getting a little delay. Let's try to see if... Well, let's guess. Well,
Here you are.
yeah, it's getting a little bit of delay because we aren't using our the best materials to communicate right now. We had to relay it through the internet. We can also make direct connections, but we didn't have the time to put it to work here. We also have GPS. It isn't getting data inside here because we don't even have cell phone signal inside. So, but there's an image from Google Earth, and it fetches image in real time. This image was put here programmatically, but it changes when the latitude and the coordinates changes. Well, we can try to demonstrate it running, but we have nothing to. Don't believe it will. Yeah, it's just okay. It isn't moving because of all the problems we discussed earlier.
So 1 minute left. So the last point here. So what's the future about this project? Well, the rover follows a modular structure. Therefore, its capabilities are only limited by our imagination and what we can do. Some of our ideas would be to simply improve its fuselage, maybe sending on atmospheric balloon and study atmosphere. Further develop in computer vision and neural network, make it learn for itself, perhaps acquire obstacle detection and avoidance. Our options are unlimited. We just have to put the same effort and dedication that we had to take LEARS from our worksheets to reality.
These are some web links that we verified. I don't know what happened. But thank you for your attention. We hope we won because we because we make a lot of effort to this project. And lots of the goals that we had set at the regional phase, we concluded in just 1 week, which shows that this is a project with caterpillars to walk. Thank you.
The difficulty in doing a rover on Mars is the communication aspect. Had you any consideration on the link that you will have between the rover and the Earth? And the Earth?
Sure. So we know there are satellites orbiting Mars as of now, and they are used to communicate with the rover. Also, as you can see, we use Wi-Fi and GPS. There are no such features in Mars, but these are proof of concepts, which means we have GPS here, but there are satellites orbiting Mars, and we can track the position of the rover using those satellites. We can also communicate with the rover, although with a big delay. I think it's 8 minutes. I'm not sure. Through these satellites, so relaying the communication through these satellites until it reaches our rover. We implemented Wi-Fi, and this Wi-Fi range can be extended to 50 kilometers if it's within line of sight. But to be in space, it would be relayed through those satellites.
Okay. Also, another question on the type of wheels you have selected. We have seen several wheels. And at the end, we see the wheels you have selected. What was the specification, trade-off consideration? Simply availability, cost, or any technical specification?
Yeah, we were most conditioned by the tight budget. We could invest more on the wheels or on other sensors. And since these wheels fit the minimal needed that we had and were the cheapest one available, seemed to be the most effective to this.
Another reason, these wheels with these wheels we can overcome obstacles like the more than the half of size of the wheels.
Okay, fine.
Yeah.
What is the job of an economist in the team?
As I said, I had lots of interests, and in economics I helped as much as I could, but I'm also interested about electronics and programming and space.
You are not a pure economist.
No, I'm not.
Okay, thank you.
If you like, we can show you more close up.
We are going to break it. Don't rely on scientists and engineers.
So, thank you. Time for the third presentation. It's a team from Greece, Astronomy Addicted. They will present the project Living with the Solar Wind. And we have Antonia Golanda, Alkistis Sapounaki, and Katerina Damopoulou, and their teacher, Mr. Ioannis Kondodinas.
Take care about fire. Slowly, it's no rush. Take your time, don't break it.
Good morning, everyone. We are the Astronomy Addicted team from Greece. Let's begin our journey from the North Pole, where we will discover the origins of the Northern Lights. The beautiful colors and extraordinary shapes inspired us to look for the scientific explanation of the phenomenon of the aurora. While researching, we've discovered that the cause of the aurora is the phenomenon of the solar wind. The solar wind is a stream of particles of plasma which consists of charged particles, mainly protons and electrons, and in lower concentration other particles like other particles. All these are emitted in the space in all directions at an average speed of about 400 kilometers per second. The sun's corona reaches a temperature of 1.1 million degrees Celsius. At such high temperatures, the sun's gravity cannot hold on to the rapidly moving particles, so they stream away from the star. Since the solar wind is a phenomenon of the sun's corona, it is important to state the identity of the particles composing the corona. At such a high temperature, such as the one I mentioned previously, helium and hydrogen are completely streamed off their electrons. Even minor elements like carbon, nitrogen, and oxygen are stripped down to bare nuclei. Only heavier trace elements like calcium and iron are able to retain some of their electrons, or a few of their electrons to be precise. It is emissions from these highly ionized particles that produce the unusual spectral lines that consist the corona. Due to the solar wind, the Sun experiences a loss of its mass by the escape of particles in a yearly basis. Namely, the phenomenon of coronal mass ejection occurs, which can be defined as a burst of gas and magnetic field arising from the magnetic field of the Sun. It is interesting to state that the mass loss per year, it is about 1.1 billion kilograms per second. It is equal into losing a mass equal to the size of the Earth every 150 million years.
When the solar wind reaches the Earth, it interacts with its magnetic field and shapes what we call the Earth's magnetosphere. Any magnetic field is caused by the motion of electrical charges. In the case of the Earth, the source of the magnetic field is not certain, but scientists have tried to trace it back to the Earth's inner core. Surrounding the inner core is a layer of liquid iron, nickel, and other metals. Differences in the temperature, pressure, and composition of these metals cause convection currents as hotter and less dense matter rises and colder and denser matter sinks. These movements, together with the swirling of the metals due to the Earth spinning, are considered the origin of the Earth's magnetic field. To a good approximation, the Earth's magnetic field can be thought of as a simple dipole with a north and south pole becoming weaker with distance. But in reality, the Earth's magnetic field interacts with the solar wind, which has its own embedded field and electric current. The solar wind compresses the Earth's day-side field to about 10 times the radius of the Earth and stretches its night-side field into a long tail called magnetotail, which may extend even further from the orbit of the Moon. Another interesting feature of the magnetic field of the Earth is the magnetopause, which is the protective boundary between the solar wind and the Earth's magnetic field. Even though the magnetopause works as a shield against the striking solar wind, some particles still can penetrate the magnetopause and leak into the Earth's magnetosphere. These particles travel and accelerate along the magnetic field lines until they reach two ring-shaped zones called auroral ovals above the north and south pole of the Earth. There, the solar wind's energetic particles collide with atmospheric particles like oxygen and nitrogen. These collisions result in different colors, different light of different frequencies, which are called the aurora, and they're typically formed 80 to 500 kilometers above the surface of the Earth. This is an artistic interpretation of the aurora by one of our friends.
We considered quite important to put in practice the theory we just mentioned. So our first idea was to construct a magnetometer which would be able to qualitatively demonstrate the non-constant nature of the magnetic field of the Earth due to the influence of the solar wind. So first we hung a magnet on a thread, then fixed a little magnet in the middle, a little mirror in the middle of the magnet, and put it into a closed jar in order to eliminate any external disturbances. After, we let the whole system settle with the magnetic field of the Earth for about a day, and then we pointed a narrow beam of light and laser light in the magnet and waited for any movement reflected on the black surface, as you can see in the photographs. However, the movement that we observed was not very big, and as a result was not observable by a naked eye. So we concluded that it was preferable to move to another experiment, and also we could have made some improvements in that one.
So our second idea was to conduct the tangent galvanometer experiment, which allowed us to graphically calculate the horizontal component of the magnetic field of the Earth, as well as demonstrate how different currents in the atmosphere may cause fluctuations to the Earth's magnetic field. As you can see in the picture, the tangent galvanometer consists of a wire loop wound around a vertical rectangular frame, a compass is put exactly at the center. And instead of compass, we used a compass application on a smartphone for better precision for our measurements. When no current flows through the wire, the compass is put that way so that it aligns with the magnetic north. But when we create a current, a magnetic field B perpendicular to the Earth's magnetic field is created. So, and as a result, the needle aligns with the resultant magnetic field R, as you can see in the diagram. In the experiment, we manipulated the current flowing through the wire and measured the angle of the deflection of the needle. This is a set of the experiment in our school's lab. You can see the ammeter, the DC power source, and the tangent galvanometer setup. This is a set of data and an example of the graph we used. As you can see in the equation of the graph, the slope contains the horizontal component of the Earth's magnetic field, so we were able to calculate it from the slope and found the value you can read on the screen. So later on, we became aware of a geomagnetic storm that had its peak on the 6th of March. And we were curious if there would be any differences in the calculated magnetic field by repeating the same experiment on the 7th and 8th of March. We came up with these values here. As you can see, there is a significant increase compared to our first trial, which was on a calm day. The increase is of about 20%. And later on, we decided to compare these values with actual magnetometer data from Potsdam, Germany. These are the graphs, and in the middle graph, the circled regions correspond to the exact times and days we took our measurements. And even though our values do not agree numerically, we can see that there is an agreement in the relative increases, as you can see here and here.
The solar wind is a phenomenon that concerns us, since it affects human activities in many ways. A solar storm could disrupt satellite communication. Satellites are used for many purposes. They transmit television signals, enable telephone communication, and provide information for weather predictions. It has been found that the solar wind degrades the efficiency of solar panels used to generate power for satellites. These solar panels contain silicon, which is vulnerable to the solar wind. As we see in the diagram, the constant rate of efficiency degradation due to the solar wind is interrupted by big drops due to solar storms. Thus, we can conclude that the solar storm accelerates the efficiency degradation of solar panels, and thus reduces the lifespan of satellites. Satellites experience an aerodynamic drag force which opposes their motion and causes them to lose altitude. The solar wind provides the upper layers of the atmosphere with energy, and thus their temperature rises. These upper layers rise higher, and they are replaced by lower layers of the atmosphere which have higher density. Satellites found in these orbits experience a higher aerodynamic drag force, and so they lose altitude more quickly. As we see in the diagram, when solar activity is close to its maximum, satellites need to be reboosted every 3 weeks, while on the other hand, when solar activity is close to its minimum, satellites are reboosted every 3 months. Therefore, there is a positive correlation between the degree of solar activity, the rate of loss of altitude experienced by satellites, and thus the corresponding need for adjusting their orbits. A severe solar storm could also adversely affect the power distribution network. The Carrington event is a solar storm that occurred in 1859. It caused telegraph operators to experience electric shocks and discharge. A solar storm of equivalent magnitude today could threaten the global communication and electricity network. A solar storm affects infrastructure in the ground and attacks multiple sites of the network at the same time, so it is very dangerous. The solar storm provides transformers with energy, which may cause them to overload. The temperature of components of the transformer that are vulnerable to excessive heating rises in the course of a few minutes, and thus these components can either be destroyed or the lifespan could be significantly reduced, which implies significant costs. As we see in the diagram, polar areas face a higher risk of being affected by a solar storm, since the magnetic field lines carrying energetic particles coming from the magnetotail end up at regions of the Earth which have high magnetic latitude. Technology today is used in all aspects of life. It is used in mass transportation, in hospitals, and in the monitoring of airplane flights, for example. Thus, we are dependent on technology, and a major blackout could threaten human life and safety. We should take measures to be protected against a solar storm. For example, there should be adequate power generators in critical places, for example, hospitals, and we should invest in the shielding of the electricity and power network against solar storms. It would also be helpful to develop a way to predict solar storms in the long term. We conducted the third experiment to demonstrate the effect of a solar storm on satellite communication. The setup of the experiment consists of two parts. The first part is a transmitter, and it is comprised of a power generator, an electronic circuit, and a laser light. The second part is the receiver, and it consists of a photodiode, an amplifier, and speakers. When everything functions properly, the LED light is on, and the laser light is also on. The laser light triggers the photodiode, as you can see in the video, and an audio signal is generated, as you can hear. When the laser light is interrupted, the audio signal is interrupted as well. We approach a charged ebonite rod to the antenna of the circuit. And as you can see, the LED light goes on and off, while the audio signal is also interrupted. The charged ebonite rod represents the solar wind as it contains charged particles. And the setup of the experiment could be parallelized with the process of satellite communication. We could imagine that a sports event is transmitted. The signal is sent to a satellite and then sent back to the Earth so that people can watch the match from their television. Based on the experiment, we have concluded that the solar storm could interrupt both the transmission of image and sound. This is our bibliography. Thank you very much.
If I may, some scientists consider the magnetic field of the Earth has not always been the same. In the past it was different, and maybe it will change more. If the Earth magnetic field were to change, what do you think would be the consequence on the life on the Earth, or the weather, or I don't know? Have you an idea?
The magnetic field actually may change every day depending on
I mean serious orientation, you know, from, for example, North Pole being in south and the country or being different direction. Not only the amplitude, you know. Serious change in the orientation. What would that affect? You have an idea?
There would certainly be differences because, for example, we know that even minor changes in the magnetic field, as we explored in our project, may have very serious impacts on technology. So such a huge change as you are describing would definitely disturb many of our systems and technologies.
Directly the life, our weather or not? Do you have an idea? You're surprised not to have idea. Right? You don't know. Okay, thank you.
You mentioned the point that you also can predict solar events because they not always happen like constantly. Do you have any idea how people in the past tried to predict solar events? In the time when there were not yet satellites?
Okay. I'm not sure if we know exactly, but we could guess that they could predict based on observations.
Have you heard of solar spots, sunspots?
For example, the geomagnetic storm that we were informed of, we became aware after it happened. But we can predict without certainty, but we can have an idea of whether a solar storm may happen from the sun's activity. For example, the sunspot number, because we know there is an 11-year cycle in the sunspot. So we can definitely have an idea, but we will never be sure until it actually takes place.
We cannot predict solar storms, however, in the long run, which would be very helpful as we can plan as far as, for example, satellite design. And also, I think that people from the past had realized that the solar activity varies in an 11-year cycle, and they had established a correlation between the change in the climate, in the average temperature of the Earth and the solar cycle, which was evident in the past, not now. And I think that Europe in the 17th, 18th century went through an era called the Little Ice Age, when the temperature had fallen significantly. And the scientists had linked this falling temperature with a reduced sunspot number at that period.
I have an additional question, because I work for the European Astronaut Center, so we don't have satellites in space, we have man in space, astronauts in space. So do you think an astronaut in space flying around the Earth and another astronaut flying around the moon, who suffers more from solar events? And why?
Yeah, since the moon is closer to the sun, it's moving rapidly around the Earth, more rapidly than the Earth around the sun. I think the astronaut in the moon would feel more the magnetic storms coming through the sun to the Earth and to the whole solar system.
Well, let me. Yeah.
Okay, but like, I'm not sure, but we could say that if the Earth has a greater magnetic field, then the variation because of the solar activity would be greater. Thus, thus a man orbiting the Earth would be more affected.
You showed before in a slide the nice picture where the sun was, and you had the Earth, and there was the magnetic field, and you also called it the magnetic shield. And
what is name of that shield?
The magnetopause.
It has a name.
Not the phenomenon belts, are just radiation belts. Well, basically, you have this magnetic shield, and you explained it well. It protects life on Earth because it acts like a protection against the storm. So it deflects all the solar particles that come, get deflected and don't hit the Earth. And that's why life on Earth is possible. And that's also the reason why astronauts flying very close to the Earth get much less radiation damage than if they would fly to Mars, for example, or fly around the moon. Because there you don't have the magnetic field and you don't have the protection. And that's also an idea why some technicians, engineers dream of creating a magnetic field around a spacecraft, because the Earth is a spacecraft and it protects us from the solar events. So that's one of the reasons. And a lot of people also believe life can only exist on a planet if that planet has a magnetic field. And Mars had an atmosphere, and this atmosphere of Mars was eroded from solar particles because it doesn't have a protection, it doesn't have a magnetic field. So it's a hugely important field that you covered, but it goes much deeper with the impacts.
But Jupiter has a field.
Yes.
So maybe
It's a gas planet. So
somebody.
No, it's enough.
yes, it's enough.
Thank you. Two free questions to be polite, let's say. Okay.
Forgot to mention that the previous team was coming from the Hellenic American College of Athens. Before we move to the fourth project, an announcement: the teams, the pioneers teams that are finishing the project, one representative, either student or teacher, could go for the short interviews in the first floor. So a colleague of mine will guide you. So we move to the fourth project, which comes from Poland, and is the team KOSMICZNI Ecology, Jakub Brach and Radoslav Paluch, from the 8th Lyceum of Marie Curie and Don Bosco School, and their teacher, Miss Jolanta Wadowska. They will present their project entitled Rubbish Bin Above Head Cleaning Space Junk from Earth Orbits.
Welcome. My name is Radosław. Here there's my friend Jakub. We are the team Space Ecologist, Kosmiczni Ekolodzy in Polish, and we would like to present you a presentation about our 8-month work on this subject.
Nowadays, around our planet orbit hundreds of man-made satellites. We can't imagine satellites. Space around Earth is filled with millions of pieces and parts of orbital debris. They are dangerous for our IT civilization. This is why we decided to take interest in our project in subject of rubbish bin above head, cleaning space junk from Earth's orbit.
At the beginning, we determined that the biggest concentration of space debris is on low Earth orbit and geostationary orbit. We decided to start cleaning our nearest space on low Earth orbit because 75% of calculated space debris is on LEO. Then we obtained more information about types of space debris. These sizable are out-of-order satellites, like this old American satellite Vanguard 1. They could also be upper parts of rocket systems and empty fuel tanks. The smaller have different origins. They also could be splinters of paint, screws and tools left by astronauts, and fragments created in collisions of satellites. In that case, orbital devices are in constant danger. More and more money is challenged for tracking and avoiding space debris. We have to remember about incredible losses in case of destroying the whole is in danger. On photography number 1, we can see damage of shuttle body made by small flake of paint. We can see how huge energy is in these fragments. And on photography number 2, we can see space trash that fell down in the territory of Saudi Arabia. We can see how huge it is, and it's endangering us, dwellers of Earth.
On the 12th of May, British astronaut Tim Pink wrote on his Twitter account about collision between ISS and small part of space debris.
So we can see this of our world. Now we would like to show you a short fragment of the movie Gravity. We can see space is a very dangerous place.
After initial research, we started developing a strategy of eliminating inadvisable trash on orbit, ITO. We acquainted ourselves with most recent ideas how to approach such problem. Then we developed our own project. We are founding our way of thinking on new phenomenon related to Kessler's syndrome.
But what is exactly the new Kessler's syndrome?
This is the phenomenon based on exponential increase of small space debris as an outcome of direct collision with other space objects. An example of such collision was 2009 collision between satellites Iridium and Cosmos on low Earth orbit. On the first picture we can see point of collision. On the second one, number of debris created in collision, and 15 minutes later.
This is why we decided to remove only sizable fragments. Anyways, big ITO seems to be easier in tracking, locating, and removing.
Next, we determined that ITO should be removed using special satellite that we called interceptor satellite.
We prepared a schema of our interceptor satellite, but before I show it, I would like to shut the lights because it will be more visible. Okay. So, our satellite will consist of the two modules, the powering module and the capturing module. In the capturing module, there will be mounted devices needed during the capturing, like cameras and sensors, the bumper, and the most important part, special movable frame, which will consist of telescopic handles, which will allow to change the size of the frame, and the net ejectors that will be moved in horizontal plane. And of course, between the net ejectors, there will be mounted the net. Inside net ejectors, there will be net stretching shafts to allow change size of the net. In the powering module, there will be tanks with xenon and chemical fuel for chemical engines, and photovoltaic cells, antennas, and the most important part, main engine, which will consist of the ion engine and the chemical boosters. We will use this hybrid because ion engine is very economical and chemical boosters will be used during the deorbitation process. We also think that it will be necessary to add the movable counterweight to let the center of mass at the same point. Without this solution, maneuvering with captured ITO would become very difficult. We prepared also a 3D model of our spacecraft. Here there is a capturing model and here there is a powering model. We can see the telescopic handles and net ejectors. Here there is a first prototype of the capturing model. We will show how it's working during the presentation. Here we can see the view from the front of our spacecraft. This is how it will be in the space. And here we can see how the telescopic handles will change its diagonals through this direction, and it will allow to catch sizable space debris. Inside net ejectors there will be mounted these shafts to allow to the sheet to be tight and to be changed the length of this net. Here you can see the interceptor satellite from the other point of view. Yes, I know about it. And here there is a ion engine and special chemical boosters which will be used during the reputation process. And here we can also see the movable counterweight to keep the center of mass at the same point.
For better view on our idea, I would like to show you capturing process step by step. Step 1, IS, we will approach to the ITO. Step 2, the frame will amplify through its diagonals to size slightly bigger than the size of the trash. Step 3, net ejectors will move in horizontal plane so as to ITO will be in the area between nets.
Our first prototype of the capturing module, created by homemade materials and the simplest tools, is able to perform this operation. So, as we can see, the net is moving in horizontal plane. We are not able to build telescopic handles by homemade materials, but this was able to create by us.
Step 4, telescopic handles will reduce its diagonals to immobilize the ITO between nets, and after capturing process, IS will pull the trash to itself.
And of course, our prototype is able to perform this operation too. Sorry.
After that, it will start slowing down to orbitate the trash.
Our next step was performing many calculations to check our ideas. On our presentation, we would like to show you only an example of our work, the calculated size of the area of photovoltaic cells. Assumption about power necessary to run our device is based on next ion thruster. It needs 7 kilowatts of power. Interceptor satellite will have other systems, so its cells are it will need increased power 7.5 kilowatts.
In case interceptor satellite would require 7.5 kilowatts of operational power, its solar panels area should be as following.
So, panels area equals power needed divided by solar constant times energy conversion efficiency of photovoltaic cells. Here are our calculations, and as we can see,
So the sufficient area of panels should be 27.6 meters square.
Of course, panels will be foldable and mounted on a frame, and it will be able to change its placement to the surface always be direct into the sun to improve the maximal power. As a method of destroying ITOs, we have chosen pushing them into Earth's atmosphere to burn them. So, IS with captured ITO will be slowing down using ion engine. You can see it's slowing down using ion engine. It will the size of radius is making smaller. It will pass not just one orbit, but it will be about 6 days when the ITO will have mass about 100 kilograms. This is an example. And on altitude 120 kilometers above Earth, our spacecraft will use chemical boosters to make the orbit elliptical with perigee on 70 kilometers above Earth. It will be already inside Earth's atmosphere, and it will guide to the destruction of the trash. We know that on altitude 120 kilometers we can release the trash and let him to make many orbits, and finally it will fall down also. But when we release it using chemical boosters and make the orbit elliptical with perigee on 70 kilometers, it will the friction with the air will be so big that it will fall down without more orbits. So it will be more safe for dwellers of Earth. So on altitude 120 kilometers, the spacecraft will release the ITO. And immediately start rotating 180 degrees and use chemical boosters to stabilize its orbit on 120 kilometers again. And for next debris target, it will go using ion engine.
From our calculations, we conclude that one IS designed to remove medium ITO up to 1000 kilograms will perform about 15 deorbitations on one fueling. It will consume about 250 kilograms of fuel, 100 kilograms of xenon, and 115 kilograms of hydrazine and dinitrogen tetroxide.
I'd like to admit that these calculations are only for one inclination, when the spacecraft will move only up and down, without changing inclination of orbit. The consumption of chemical fuel is representing by dots because it will be just impulses, not still consumption like in the xenon. And SpaceX new rocket Falcon 9 is able to carry 16 tons of fuel on orbit. Our hybrid of ion engine and chemical boosters is a very economical thruster. 16 tons of fuel will be sufficient for 74 consecutive fuelings of our spacecraft.
We take option that adding more interceptor satellites will be necessary to make this project successful. Project of removing space debris should be an international action similar to International Space Station project.
We think that each single country would participate in this endeavor. We have to remember about incredible losses in case of destroying the whole satellite network and probability of losing most of 21st century profits. Costs of removing this risk compared to such a danger will be a great investment into our future and civilization development, which will pay us back in 100%. So the problem of rubbish bin is really important. However, public opinion and media basically ignore this increasing problem. Work on this subject, knowledge, developed our passion astronomy and physics, and engage us with solving real problem of our world.
We are happy with effects of our work. During development of this enterprise, we often faced many problems that extend our creativity. As we are planning to expand our project to removing trash from geostationary orbit in the nearest future.
After all, we have to remember that if we want to explore space, we need to clean it at first. Thank you for your attention.
So let me just summarize to see if I understood well. So you want to catch space debris and you want to fly it down to 120 kilometers height, and then you drop it and you accelerate your satellite again to fly up and catch the next one. Is that correct?
Yes, we accelerate them, the spacecraft, to prevent falling down on Earth. It's the chemical boosters will only stabilize on 120 kilometers, and for our ITO it will go using ion engine. And
okay, but at around 120 kilometers the friction might already be so high that this one also gets...
Yes, but it will be able to do many orbits before space. When something is falling down from 120 kilometers above Earth, it is able to do many orbits, but our spacecraft will be able to, after a few minutes or several minutes, to rotate and use chemical engines to escape from this area in space.
Okay. You showed some pictures where you saw like impact of space debris on spacecrafts.
Yes.
And these looks like bullets being fired at the surface.
Yes.
What do you think will happen to your net if such a high velocity piece of debris impacts your net? Don't you expect that there will also be a hole in that?
I think that the net, our spacecraft is designed to remove sizable fragments. So even if this small debris, like splinter of paint, will make a small hole in this net, it will be projected to live after this impact, and will be able to catch other space debris because they will be bigger than this hole, and it will doesn't change the way the net will be working.
Another approach to clearing debris is avoiding debris. What do you think, like, what is more important, like removing debris or changing the rules for launch to make sure that we don't even get that much trash up there?
Of course, we have to clean orbit because the trash is already there. We also have to prevent creation of new space debris by using, as you said, using the satellites that will be, for example, deorbitate itself after braking or something like that. But it's more important to remove the debris that are already there and they are endangering, and related and Kessler's syndrome will be making more smaller space debris that will be more problem than the big space debris, because small we can't track exactly the small space debris, and they also have big energy and they more dangerous than big ITO we will be removing, and big ITO are the source of this smaller. So I think
He's going to ask the question.
so many questions. Maybe a question out of your work. What is the legal frame? Are we authorized to go in orbit, take one supposed debris, and bring it back to the Earth? Who is owning the debris? Are you authorized to take a piece of satellite somewhere and take it down to the Earth?
Satellites has its owners.
So,
because, for example, there are satellites of USA, satellites of private companies, satellites of Russia, 2 satellites of Poland, and everybody should. This should be an international action, and every one of us is using satellites. So every one of us is a satellite user, and costs of cleaning space. We everybody making this space debris out. When we watch TV, we use satellites, and satellites sometimes broke. And
do you imagine easily achievable the fact that, let me just give an example and forget just after the names. China go in space, take a US satellite and does something with the satellite, possibly send it to the Earth, or possibly do something else with the satellite.
This is why.
What would say the US?
I understand.
For that?
This is why this will not be making by countries, but by companies, like I said, SpaceX, and this is why this is not a mission for one country. This is not a mission for one company. This is an internationally intercompany. Yes, to prevent space debris formation and to clean the space above us.
No. And how do you refuel your satellite? Because going up and down, that's a lot of. I saw your calculations. That's hundreds of kilos of fuel, and each kilo you put up in space costs a fortune.
So costs of carrying 16 tons of fuel in, for example, four tanks are about $4,000 per 1 kilogram. We think that the interceptor satellite will be connected with the tank during carrying it on the orbit. Then, when it will be released and it will separate with the tank, it will leave the tank on altitude, for example, 300 kilometers above Earth, and it will start cleaning. When the fuel will be low, it will change its altitude to 300 kilometers and tank from this tank. We think that one tank will be enough to drive our satellite during this whole project. And after cleaning one inclination above Earth, it will deorbitate itself, and the tank also will deorbitate and will not do space debris also. We're real space ecologists. Thank you.
We have the 5th team from the United Kingdom, is Mission Red 2030 from Hockerhill Anglo-European College, and they're presenting Rebecca Hayward and Eleanor Ivy. Their teacher was Mr. Guy Dinwiddie.
Hello, we're Rebecca Hayward and Eleanor Ivy from Hochul Anglo-European College, and we are very pleased to be here in Europe today. We selected the category Human Beings on Mars and decided to produce a brochure for prospective travellers to Mars. We branded the project Mission Red 2030 and gave an overview of what lies ahead for those leaving Earth, including a map of the landing sites. We have also included a fictional video of our traveller being interviewed as she is to lift off to life on Mars and discusses the emotional and physical side of the journey. The interview resumes 8 months later with her arrival on Mars, showing her disorientated, stressed by the effects of the journey, closed in with the same people, and includes a time delay affecting communication back on Earth.
The spacesuits that will be used to protect the humans whilst they're on Mars are a vital part of this mission because they would be the thing that protect us from the harsh conditions that we have highlighted already. The suits would require a stable internal pressure and a steady supply of oxygen in order to allow the user to breathe. Obviously there is a difference in gravity from Mars and Earth, and over time the human race would probably adapt to this. But however, for the first 2 to 3 generations, aid would probably be needed to help them get used to it, such as the skin suit that ESA is currently developing as a exercise tool designed to reduce back pain in astronauts.
We start with an introduction which contains general interesting information about what you could see on the red planet, such as Olympus Mons or the Galley crater, also known as the smiley face crater, which we rather like.
So changes would be necessary for life on Mars because humans are currently acclimatized to the conditions on Earth, and obviously Mars is a very different planet. Some of the differences, as we've highlighted in this article, are the atmosphere, the water supply, and the temperature. The atmosphere is very important because obviously the atmosphere on Mars is too thin for humans to breathe, so they would need aid, as we said with the spacesuit. The water supply is significantly less on Mars, and most of it's frozen when there is some. And it's frozen because of the lower temperatures. I think their average temperature is about 60 degrees Celsius lower than that on Earth.
On Mars, you'll be able to enjoy ice clouds similar to Earth's cirrus clouds, although they may be hidden by the permanent veil of dust that makes the sky look orange during the day. However, at sunrise and sunset, the sky is blue due to the greatest depth of atmosphere and dust. The Martian year is nearly twice as long as Earth's, lasting 322 days longer, but due to the tilted axis, visitors would still experience winter and summer the same as on Earth. Because of the longer year, the months are also very long, so we decided to come up with new names for the 12 months on Mars, named after constellations you can see here on Earth. Although the conditions on Mars are fairly close to Earth in terms of temperature, unlike other planets or the Moon, they are still harsh for human life to exist. To experience atmospheric pressure similar to the low altitude on Mars, you would have to visit Antarctica. The sparse Martian atmosphere means that what little temperature increase that does occur during the day is soon lost at night, plunging up to 100 degrees Celsius in extreme conditions. Mars has no global magnetic field, and its thin atmosphere, with its thin atmosphere, a significant amount of ionizing radiation reaches the surface. Radiation levels in orbit above Mars are almost 2.5% times higher than on the International Space Station.
As you can see in the brochure, we have considered different ways to generate energy, as this would be necessary for a human settlement on Mars. The 2 options for generating energy that we decided to focus on were solar photovoltaic panels and radioisotope thermoelectric generators. There are many disadvantages and advantages of each method, but one of the main disadvantages of using the solar panels is the fact that obviously dust storms on Mars are quite prominent, and the dust could settle on the panels and block direct sunlight from reaching them in order so that they wouldn't be able to generate energy anymore. Whereas the radioisotope thermoelectric generators do not rely on sunlight, though they can provide a constant stream of energy, which is probably better for a human settlement.
On this page, we have included some of the rules we think would be necessary to have on Mars to maintain stability and prevent running out of the limited supplies we would have on the planet, most of which would have to be transported there from Earth. We have also included a daily routine. We believe that it would be necessary to have officials, farmers, medical staff, manual labourers, explorers and technicians at least in our Martian colony so that it's fully functional and able to expand and grow as more and more people begin to arrive on the planet. Each of these groups would have a timetable that consists of their meals, hygiene, work, sleep and training, among the other chores that need to be done around the colony. We've also mentioned that there would need to be a night shift, as, for example, you would need to have medical staff at all hours.
One aspect of the Mission Red 2030 project is the housing and where humans would stay once they're on Mars. For this, we have come up with the idea of using the beam inflatable pods, which were successfully used on the ISS in 2016. The pods have enough space for 6 members of the crew, allowing them to live and work in the same area, whilst also being able to withstand harsh conditions, extreme temperatures, and any impact from debris during landing or the Martian dust storms.
As the beam pods do not last forever, we would need a more permanent solution, which can be found in NASA's High Seas Habitat project, which we would like to situate on the northern slopes of Mauna Loa. They are large domes with 2 floors, which each have a kitchen, dining area, bathroom, personal lab, and exercise area, with an additional workshop. This will improve the standard of living and working facilities on Mars.
The journey to Mars will result in decreased muscle mass, reduced aerobic capacity, and badly affect bone density. This page is a brief insight into the importance of physical exercise to combat these issues during the journey to Mars and once settled on Mars. Using the study of astronauts on the ISS, we have learnt that it's important to include regular resistance training once you're on Mars and during the journey to combat these conditions. Diet is very important while you're in space because you've got to eat enough to stay healthy even though there isn't enough food, because whilst in space you'll become more susceptible to illness. Food and drink will come in with each new supply rocket in the short term, whilst the settlers on Mars would be trying to make themselves self-sufficient and building an infrastructure in order to be able to be self-sufficient. The soil on Mars could be too rich in iron oxides to grow some crops, and any crops that do grow may lack colour and they won't be very appealing to eat.
We thought that 3D printing would be a very good idea in our Martian colony, due to it being very quick, easy and cost effective. There is currently lots of research going into 3D printing in space, and it's been found that it works very similarly in space as it does on Earth. This is very useful, as it means we could create a lighter rocket, spare parts, medical equipment, and even replacement body parts. Also, this would be a good place to have recycling, as our resources won't last forever.
Mission Red 2030 is designed to be fun and enjoyable for children, whilst also keeping them fit and healthy. With an extra 40 minutes each day to fill, they will have plenty of time for this. This is what influenced us to come up with the idea of an app that would keep them healthy whilst also educating them. The Space Pro app involves using a device as a tennis racket on different planets trying to hit a ball. This would teach them about the forces of gravity on each planet and also keep them doing this resistance training that is so important whilst on Mars. On Earth, you would be able to hit a ball a reasonable distance quite easily. If you were to do the same on the Moon, it would take longer for the ball to travel that distance because obviously the gravity is lower. On Jupiter, assuming you could actually lift the racket, the ball would not travel so far because the gravity on Jupiter is almost double that on Earth. So the ball would fall much quicker, so you wouldn't be able to get the distance.
At this point in time, in 2030, Curiosity would have finished their time on Mars and would now be a prized museum piece on our planet. Mars rovers are used to feed back information about the red planet to humans, crucial in a time when humans could not access the planet. The nuclear-powered rovers provide vital analysis of Mars, giving us the information to enable us to adapt to the extreme environment in 2030, as in the brochure. Such as in 2016, when Curiosity discovered high levels of manganese oxides using her laser-firing instruments, indicating that there was a higher level of oxygen when groundwater was present in the Galley crater area. The rover's other tasks include research into radiation, geochemical composition, history, and biology. We have also included the Mars 2020 rover, which is supposed to allow geological samples from Mars to be brought home to Earth so that scientists may analyse them.
The Mars Museum explores bringing the idea of relatively new Earth technology to Earth, from Earth to Mars. It would use virtual reality to bring aspects of life that the human settlers will have already experienced on Earth to their new home in Mars. We have used the phrasing a fun soul out because obviously a solar day on Mars is longer than a solar day on Earth, and therefore it is called a soul to differentiate it from the length of time of a day on Earth. It would be so exciting to be able to do these things that you do on Earth, like visit the ruins of Egypt, the Egyptian pyramids, and go to like a Michael Jackson concert or something.
This time we've also added a map to our brochure, which is a map of the area around our proposed landing site, chosen due to its low elevation, safety and easy access, because it is in an equatorial region which uses less delta V to land. There is maximum distance between the orbit and the ground for a safe landing, and it is near to mountains and canyons which provide a good base for research. Here is a brief look at some of the effects the journey to Mars would have on us.
As an astronomer, I've always admired the planets and the stars that seem so far away, untouchable. Now we've developed technology perfect for travelling and living on the planet Mars. When I heard that Mission Red were going ahead with their venture, my family and I could not wait to get on board.
So you're taking your family, but there must still be some things you'll have to leave behind on Earth. What do you think you'll miss most about your old planet?
There are many things I'll miss, from the blue sky to all my friends back home. Mars is such a different planet, and though this is exciting, it's also a daunting prospect, as it will be just my family and a few others embarking on this new adventure alone.
So could you explain to viewers what will be taking place tomorrow and throughout your flight to Mars?
We'll lift off tomorrow on a commercial flight. There'll be around 30 of us on the rocket, all with different tasks ahead. After we lift off, we will orbit around Earth until the orbits align, and we will join the orbit of Mars and decelerate, so the spacecraft is drawn into Mars by its gravity. The entire flight will last about 8 months, so we have to eat and exercise properly so that we stay fit and healthy for our arrival.
What's the most exciting thing about your voyage to Mars?
Oh, it's so hard to choose, but if I had to say one thing, it would be exploring a new planet as never before. It has been my dream since I was a little girl to explore the universe, and this is just one small step.
At the moment, trips to Mars are only one way. How do you feel about this?
Honestly, I don't mind. I think it will be wonderful to have a fresh start on a beautiful new planet, and I can't wait. I'm fed up with the way Earth has been treated and love the idea of starting again.
Thank you for your time with Mission Red. We hope you enjoy your flight, and we will see you in about 8 months.
Thank you. Goodbye.
Welcome to Mars. Unfortunately, our conversation will be a little stilted due to the 15-minute time gap we'll have between Mars and Earth. How are you feeling?
I'm very tired and rather heavy. I haven't been in gravity for quite a while now, so it feels quite strange to be back on steady ground. Not only was the flight physically challenging, but mentally too. Even the time difference in this interview is tiring. And can you hear the sound? It's less now, but during the flight it was so loud. Who knew noise pollution could be so annoying?
I'm sure you'll get used to it in no time. The gravity there is even lower than on Earth. What was your favourite part about the flight?
Well, although it was very tiring, I quite enjoyed the exercises that kept me fit and healthy while I was in zero gravity.
A fun experience. However, there must have been some bad bits.
I can't say the food was amazing, a bit tasteless and kind of fishy. But it was also very claustrophobic on the ship, and some of the people on board were so annoying.
Well, you'll be out very soon. When you finally get out of the ship, what are you most excited to do?
Honestly, I just want to get off the ship. I'm also looking forward to sleeping in a proper bed. It's been a long time.
And what would you recommend to your future Mission Red travellers?
Exercise as much as possible to keep your health at the optimum level, as it can be very hard to function properly in gravity after all training to prepare me for how hard the trip's going to be. I'm so glad it's over. Good luck.
We're so glad that you enjoyed your Mission Red voyage, and we hope to see you in the future. We really hope you enjoy your time on Mars.
Thank you for listening.
One question or two. I understand you are the first ever company organizing trip to Mars for private, well, tourists and so on. Could you tell me in 2 or 3 words, or a bit more if you wish, why I should go there? But unfortunately, I don't speak English. I don't understand English. I speak only French and Spanish. Could you do something for me? I know they speak Spanish. Vale. En español, por ejemplo. O en francés, si vous voulez.
Un voyage sera
I have also a question. You were traveling to Mars, you stayed on Earth, so the question is to you, because I mean, you experienced the trip. You look very tired and exhausted, so what would be a recommendation to future space travelers? What should they do apart from doing sports to stay healthy, to stay mentally fit? How do you how do you keep the good spirits during such a long journey in such a confined environment?
I think to keep in good spirits, you need to talk to people you actually like, and also get some alone time as well. So, because being around loads of people for a really long amount of time it gets tiring after a while, and you need to go back into yourself and sort of have a rest and then come back and enjoy yourself with other people. So obviously it's quite difficult to be by yourself in a small space, but that's what I'd probably recommend. Yeah.
Oh, okay, so you are tourist guides to Mars, and I want to travel with you. But what if I decide to stay on Mars and don't return to Earth?
Yeah, this is a one-way mission, but there's been we were thinking that if it were to carry on and if there were to be more research done into it, there has been research done that does propose that you could come back. But at the moment, obviously, we only have the resources to do a one-way mission.
It's a one-way mission then.
Yeah, for the moment.
Okay, now the 6th project is from Germany. Is AlphaTeam. It's the last before the break. Okay, it's the AlphaTeam. They are coming from Koblenz, Max von Laue Gymnasium. Unfortunately, the second student couldn't be with us today, so it will be only Lucas Mohr. His teammate Alexander Hake is arriving this evening due to another commitment he had. And their teacher is Mr. Sven Hebenstadt. Are they in the room or not? They are carrying their project, so they are with us. And after this presentation, we'll have a break, and then we will have the last three.
Hello, I'm Lucas Moore, and I'm a member of the team. Oh, okay. Hello, I'm Lucas Moore from team Magnet Rocket out of Germany, and my team member Alexander, he's in Munich. He will come later, not for the presentation, maybe you can see him. And I want to tell you something about our project. Our idea was to make a system to can shoot projectiles, something like a rocket, from a place to another place in orbit without use of chemical fuel. So at first we had the idea to build a railgun. I will tell you what a railgun should be. In internet you see a picture like this. This should show how a railgun will work. We have here two cable. Here can got a current, also in this direction, this black. And therefore, because of the Lorentz force, we have a current, this flow, because we have here another thing. So the current can flow this way. So we have a current, and so out of this we have a magnetic field. It's in blue here on this line. It's in 90 degrees to the current, and out of this is the Lorentz force. This is green, and this Lorentz force should move our projectile into this direction. So at first we tried to build something like this. Here's our first prototype. It's just a rail out of a model railway, and so we have here the two metal things where the current can flow. Here the bogie, we have also metal, there the current can go this way. And at the end we have cables. We could put the accumulator on this, and so we have a current, and out of this we have a magnetic field, and so it should happen that this wagon moved in this direction. So we tested, and what happened? It happened nothing what we expected. There was some sparks, and the rails started to glow. We had the plastic, you can see, is melting, and the bogie welds together with the rail. So what is wrong? We don't know. So we make an experiment in laboratory. So I think, yeah, that's correct. And show what are the components of the Lorentz force. And so we have here a conductor loop. You see it here. There's a current inside. And also we have a magnetic field out of these coils with two pole tools. The conductor loop is in between here in 90 degrees. And at the top is the force sensor, and we want to show how much force we can produce in laboratory, because this force is the same force who will give speed to our wing. And after we done this experiment, we came to a conclusion that we could make at best our system if we do permanent magnets on top and then the bottom to make the magnetic field more working. So we did the same as before, something like this. So we had the magnets on top, and what happened then? The same we before. We have just sparks and fire and light and smoke, and we don't know why it is. We have shown in the internet it should go there. The US military have the same system, and they share, so it must be, and we don't know why. Maybe they will tell us our secret or not. So we have here you can see the permanent sticks here, and at the bottom are also permanent sticks, and then we don't know what to do. So we have go in the laboratory and make something what must work. We had a coil, you can see it here, with an iron core inside, and on the wagon
By the way, I think I remember some German-French institute somewhere in Alsace, maybe, or close to the border, has been working for years on this sort of equipment. Do you know about that, what they do, or what they have been able to develop?
I just know the US military. The US military has a system.
It's